But here we go. I have worksheet number 3, which was, John, I agree, the easiest out of all of homework. We're going to fill in real fast. Actually, we have the answer key. I don't think you need me to fill in. But worksheet number 3, I think I have it right here somewhere. Boop, 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 boop. We're going to talk about it really quickly. Make sure you guys don't have any questions on worksheet number 3. Fill in our notes, fill in the blanks. Maybe peek at really quickly examples 2 and 3. I'm trying to give a couple pointers. But once again, I'm not spot checking this until tomorrow. Attempted in pencil and graded in pen and corrected if it needed to be. Okay. We know absolute value makes all numbers non-negative. Okay, whatever. They're saying 0 or positive. 0 stays the same. Positive stays the same. Negative flips. That's why they're saying non-negative, because 0 is technically neither positive nor negative. And then, this is just a reminder from transformations in pre-cal. If you take an absolute value of an entire function, like a parabola, for instance, if he's below the origin, remember that bottom part flips up, becomes like that weird W thing. Anyway, so just reminding that if you take an absolute value of an entire function, the y's cannot be negative, and so they will have that portion of the graph will have a vertical reflection. But otherwise, you guys are just saying, like, hey, they stay the same. And if they stay the same velocity, then positive numbers increasing, speed will also be, well, speed's always positive, but speed will also be increasing. But in between speed increasing and velocity increasing is this extra little line that says, wait a minute, since velocity is increasing, acceleration is positive. And that might not have made much sense to you guys until you got to the very end of this worksheet, because you were just like, okay, whatever, negatives become positive. I see velocity is negative and going more negative, hence decreasing. Velocity is decreasing, which means acceleration is negative. And by the way, looking at my speeds, hey, look, they're increasing. Now, that might be something that jumped off the page to you, or it might not have been. But isn't it weird that velocity is decreasing, but speed is increasing? Does that sound weird in your head at all? Because if velocity is decreasing, what do you automatically think? Oh, you must be slowing down. But is that true? What does decreasing mean? Guys, check it. What does decreasing mean in this sense? If velocity is negative, what does decreasing mean to the speed, or to how fast, or to the magnitude? Velocity is negative and decreasing, hence you are speeding up in the negative direction. Do you see it? So it's weird, because the word decreasing, oh, slowing, no. If you have negative numbers that are decreasing, that are going down, that means my speed is going up, because I'm going down more and more, more and more negative, more and more negative, more and more. The speed is increasing. That's weird. This one, I have negative numbers that flip to positive. Velocity is negative and increasing. Oh, speeding up. No, if you have negative numbers increasing, aren't you getting closer to 0? Velocity is negative and increasing. Okay, since it's increasing, acceleration is positive. You're slowing down. It looks obvious in the graph, but it might be confusing otherwise. Sorry, you guys checking your graph? This one, the negatives flip up. Oh yeah, of course it's increasing speed. Absolute value of velocity flips up. Oh, of course speed is decreasing. It makes sense in the picture, but the words will look so confusing because velocity increasing. Negative velocity is increasing. I'm slowing down. In this last one, I have positive and decreasing. It was like the first one in the sense that it's most intuitive, because positive numbers, when they increase or decrease, we're used to those numbers. And it's like, oh yeah, okay, you're getting closer and closer to 0, so I'm slowing down, which is exactly what you should have seen. So at the very end, it said, okay, go back and consider, when is speed increasing? I would box that, I would circle that, when speed is increasing. Okay, that's what's in our notes. That's what's in our notes that we're supposed to be filling in. When does speed increase? And what did you guys notice if you did it correctly about the situations 1 and 2 where speed did increase? What was going on with velocity and acceleration? They're working together. So if velocity is positive, I'm moving to the right. If acceleration is positive, I'm pushing to the right in some senses. And so moving to the right, pushing to the right, I'm going to speed up. If velocity is negative, I'm moving to the left. If acceleration is negative, I'm pushing to the left. Moving to the left, pushing to the left, speed up. But what's true if they have opposite signs? Velocity is negative and increasing. Negative is, but increasing numerically is, but how does, they're working against each other. I'm going to slow down. Velocity is positive, but decreasing. Okay, that's so intuitive. But once again, the signs are working opposite each other. I'm slowing down. So, in your notes, how should you fill this in? Speed increases, aka, the AP can put it either way. Speed increasing, or it can say speeding up. Same thing with you guys. You can say speed is increasing, or you're speeding up, or getting faster. Only when velocity and acceleration have the same sign. And if you want, it might be very helpful to put in parentheses, because once we put away this packet for good in a couple weeks, once we put this packet away, it might be really easy to forget this. So if velocity is positive and increasing, because remember, if velocity is increasing, acceleration is positive. If velocity is negative and, I know it's weird, but decreasing. Velocity is positive and increasing, or negative and decreasing, I'm speeding up. It's another way of kind of fleshing out acceleration being positive, acceleration being negative. That means velocity is increasing or decreasing. And then speed is going to decrease, aka my object is going to be slowing down. And velocity and acceleration have, you guys just saw it, opposite signs. Now, I'll probably have a little baby pop quiz that won't really count as much. It's just more for you guys to be like, do I really understand it at the very beginning of tomorrow about speed increasing and decreasing. It just has little baby scenarios of when this, fill in the blank. I'm speeding up and acceleration is positive. What must velocity be? I'm speeding up and acceleration is positive. What must velocity be? Positive. There's going to be kind of like that terminology, and just see if you can fill in the blank. It's not going to hurt your grade. It's not even going to go into your grade. It's just more of a little baby, hey, can you do it? To give you, well, some of you are still taking tonight to kind of finish up this whole grading, correcting thing. So we'll do that at the beginning of class tomorrow, just a quick little handout. But opposite signs to help you could say something like positive and decreasing. That's intuitive. The one that's not intuitive is negative and increasing. Oh, that's just weird. They're working against each other. Okay, worksheet number 3. The most important thing for actually taking notes and having like a concept of certain phrase that we know what to do with if the AP were to ever ask us. Speeding up, slowing down, speed increasing, speed decreasing, velocity, acceleration, signs. Wait, signs. How do we ever think about signs? Well, quick reminder, quick note at the bottom. Yeah? To check speed, increasing, decreasing, compare velocity and acceleration sign charts. That's how we do it, right? That's how we do it. That's how we check signs. Which means we'll have to do a first and second derivative sign chart kind of on top of each other and compare when they're the same and when they're different. Okay, going back then. There is more to this packet for sure, but going back. You did technically have example number 2 and example number 3. We did example number 1 entirely together. Ending in MBT, remember we made it harder than even they would have done because we used MBT instead of roles, kind of. And I think they might have done that too, to be honest. Because if you notice, they went into like the IVT and they kind of talked about MBT. Anyway, they made it a bit complicated, but they kind of did ours too, just in a probably a much better way than we did. But we didn't just have example 1. We also had example 2 and example 3. I'm going to go ahead and pull it up on here, though. I think I have it. Yeah. Was there anything as you guys were, for those of you that tried it and graded it, remember, for those of you that are just like, yeah, I looked at it and I got stuck, and I'm not judging you, I'm just saying you needed to work a little bit harder. But for those of you that tried it, graded it, and you're like, I don't quite, were there any questions you wanted to ask me, clarifications you wanted to ask me about example 2 for right now? Either places that you got stuck and you can verbalize it and say, I didn't know how to, what it meant by. Clarification questions or correction questions. Okay, I'm going to ask you the exact same thing tomorrow. So if you don't have any clarification, like what is it asking, what am I supposed to look at, form those questions tonight, maybe write them down, but clarification questions, but also correction questions. The answer key was online, you could have read through. I'm going to go ahead and go to example number 3. Was there a part that I let you guys skip for this one? No, that was the next one, right? Can you guys go ahead and put a line through number 6? Some of you might have still tried it, but I don't want to answer questions on it until we cover the rest of motion, which is in about 2 sections. Section 4.1b is the intro to motion, with integration, I should say. But in a couple sections, we go a little deeper in motion, and that will help us. Number 6, we need to talk about the idea of area. And we haven't gotten there yet. So just put a little line through it. Just, you can ignore it for right now. Example number 3, though. Any questions, clarification, or correction questions? Clarification on what they're asking, what you're supposed to be thinking, or correction questions. Why is the answer this? Yeah, why? Number 3. Okay, and then number 4 we crossed out, right? So what did they give us? What kind of function are we dealing with? I mean, A, it's a function, but B, what kind of function? Position. Okay, so when it says moving to the left, we have to figure out in our minds who we want to look at. Moving to the left, what tells us about which direction I'm moving? Sign of velocity. So, first of all, I need to figure out my velocity function if you haven't yet already. Velocity is equal to 3t squared minus 12t plus 9. I just notice a 3 in everything, so to make my life easier, I'm pretty sure this will be helpful. And then if you're really snazzy, you're like, wait a minute, I think I can factor that. Anyway, moving to the left. If I want to consider the signs of anything, and I can't just plug in, because it doesn't tell me like at t equals 2 when I just plug it in and figure out the sign. I need to consider all the signs. To consider all the signs, what do I need to make? Sign chart. So I'm going to make a sign chart of, and I'm going to do it off to the side. Velocity. Now I'm not starting at 0. I'm not ending at something like 5 or 8 or 12, because they didn't give me any sort of domain. So I'm like, well, it's a polynomial, so I guess all real numbers. If they wanted me to think of something else, they should have done that. Why am I putting 1 and 3 in here? They're the crits, aka they're the zeros of my rate function, aka they're my resting points, the points in between which the signs of velocity can change or my direction can switch. And so if I'm trying to figure out if my particle is moving to the right or to the left, I need to think about velocity signs. I can plug in something like 0, a negative times a negative is a positive. Something like 2, ooh, one's a positive, one's a negative, and something like 4, they're both positive. And now I can know moving to the right, moving to the left, moving to the right. When is the particle moving to the left? The particle is moving left for all t within. Why am I going to do an open interval? Everything between 1 and 3, but not 1, not 3. No brackets, only parentheses. Is that 1 and 3 decimal? At 1 and 3, it's stopped. It's not moving. Yeah. But in between 1 and 3, well, he's moving to the right. He stopped. Oh, he's moving back. So as soon as 1 passes, as soon as 3 is over, he's going the different direction. At 1, at 3, momentary stop. And then remember number 4 is okay, I'm going to ask the exact same questions tomorrow. Any clarifications? Is there any of the wording, any of the question, any of the given information, any of what you're supposed to be thinking, is that confusing? Clarification, but also correction. Is there anything that you're not sure why the answer is what it is? Or you need some further explanation for what work was done? I'm going to ask that tomorrow for examples 2 and 3. Sound good? Okay, and then I'm going to do a spot check. After take that little baby speed, increasing speed, decreasing idea pop quiz. All right, guys, let's go ahead and transition into our notes section 4.2. I'm not trying to be tricky. I'm not trying to like avoid the homework that you guys did. I'm just trying to be realistic, but I know some of you, because of a lack of questions today, I know some of you need to try a little harder on that work or on that homework. Or get your colored pen out and actually correct so you have questions to ask. Okie doke. Oh my goodness, there are sigmas on the page. There are sigmas on the page. Which, to be honest, in CalcAB are barely necessary. Barely necessary for you to totally understand. In CalcBC, we talk a little bit more about the limit definition of an integral. In AB, we're going to have a forever card on it, the limit definition of an integral, but we're not going to have to solve it by hand.
Yay.
And sigmas are really only used in this area idea, only really used in the idea behind an integral. And the nice thing is, for you guys, Jared, our OChem tutor guy, at least according to period, is that you guys?
Yeah.
You've already kind of gotten, at least, you've heard a little bit about an integral and area have something to do with each other. And the nice thing is, at the very, very, very beginning of the year, you're just writing down sigma properties for a second. Don't worry, not a forever card. Once again, sigmas are not a huge, huge, huge tool that you need to use a lot in CalcAB foundational calculus. But even at the beginning of the year, we did a tangent line, well, secant lines that got to a tangent line, and we did an area, well, rectangles that approximated an area. Yeah, wasn't that the first day class?
Yeah.
Maybe the second day class? Anyway, I've been preparing you guys for this, or at least foreshadowing that it's coming for a while now. Maybe since the very beginning. So, area. Well, before we get to area, I don't know, some of you guys might take the SAT sometime soon, or already have. Sigmas, every now and then they show up. Maybe it's not a bad idea that we at least know the basics. A sigma, when you have a bottom bound and a top bound, doesn't that mean that you plug in stuff, right? And you follow whatever the little function is inside the sigma, whatever the argument is. And you just do it for all positive integers in between the lower and upper bounds, including the bounds. Now, it can be a little tedious to write it out by hand, right? But if you can throw it in a sigma and be like, hey, computer, help me, please. A lot nicer. Sure. Repeated addition can be summarized into a sigma, which is really nice. And it's especially nice if we're doing something like a, oh my goodness. What am I not doing in number 2?
You don't have to end out.
I'm not ending because what's the top say?
We should say.
Now this one's a little bit tricky because this one is actually going to equal infinity, because if you add 0 plus 1 plus 4 plus 9 plus 16 plus 25, it's just going to be ever expanding. And what symbol denotes an ever expanding quantity? Aha! So I mean, that's not super exciting, it's just infinity. But once again, I can condense an infinite addition into one sigma notation, which is kind of cool. And it might be kind of useful, especially in what we're about to be seeing, especially if you remember something to do with, oh hey, at the beginning of the year we had to add all those rectangles. That was kind of annoying. Down here, properties. If you have a sigma, if there's a constant next to like an nth term formula, nth term a sub n, that had to do with sequences and series and pre-count. This one says a sub k, sometimes it's a sub I or a sub n. If you have a constant c, you can pull it out. Number 2, if you have like an addition or subtraction, you can split it up. Because if you add like all of these guys, plus like a sub 1 plus b sub 1, a sub 2 plus b sub 2, a sub 3 plus b sub 3, or a sub 1, a sub 2, a sub 3, b sub 1, b sub 2, b sub 3. Addition is commutative, so I can totally do that. Subtraction is commutative. I can totally do that. I can switch around the orders. And that just kind of, to be honest, is fundamental to some of those integration rules that we've talked about, because at their cores, all integrals are sigmas. With infinite bounds. What? All integrals, all definite integrals. Oh, bottom and top bounds, like a beginning and an ending. All definite integrals are technically sigmas with an infinite bound, which is weird because I just said they have beginnings and endings. Kyle, go ahead.
Correct me if I'm wrong. Did you say that subtraction is commutative?
Subtraction, when seen as adding opposites, can be commutative. Thank you. Subtraction, when seen as adding opposites, is commutative. Yeah. Thank you. Because this subtraction will be distributed across all of those additions, and so technically we'll be fine. But yeah, thanks. That's dangerous what I just said. Okay, so answering the second major question of calculus. Maybe you remember there were two from the very beginning of the year. Maybe you don't. The first one was slope of a tangent line, basically instantaneous rate. How to find the rate at one point, the slope at one point. The second big question is the area problem. Find the area between a function and the horizontal axis for a given interval. Now, maybe that's the big question that's answered, or maybe that's the answer to another big question. But either way, what needs to happen for a definite integral is finding the area between a function and the horizontal axis for a given x interval. Why do we need calculus? Sometimes we don't. Why do we need calculus? Sometimes we don't. That has to start there. Sometimes we don't. If the area is a common geometric figure. Like, what if it's triangular, or trapezoidal, or rectangular? What if it's circular, like a half circle, or a quarter circle? Bless you. What if it's circular, or even a part of a circle? Sometimes we don't need calculus, to be honest. We know how to do a lot of areas, but do we know how to do all areas? Nope. If it's not a circle, if it's not a triangle, if it's not a square, if it's not a trapezoid, if it's not a rectangle, if it's not some sort of circular sector, like a part of a circle, we don't know how to find the area. So the area problem says, find the area between, and then we have this, oh, sometimes it's just common geometry, but sometimes it's not. That's why we need calculus. I'm going to go ahead and dual screen because most of you probably have the main core of this page, or the main information from this page. I want you guys to try to graph these two figures. I want you guys to try to graph these two figures. I took away the underline because technically the underline's at the very top, but I am going to make this bold. The one on top gives the function negative 2x plus 3. It's a line. And the axis is a line. I wonder if we can find the area always between any two lines. The top is a linear function. The axis is a line. I wonder if we can always find the area between two lines. The bottom, not a line. It's a parabola. You guys remember how to graph a line? You have an intercept, you go down 2, over 1, down 2, over 1. Now, do you notice you're not just supposed to be graphing the function, but you're also supposed to be thinking about an interval?
Yeah.
Not a point, an interval, a beginning and an ending. These are technically, if you want to think about it, these are x intervals, which we've been using all year for like increasing and decreasing, etc. So if I'm going between 0 and 1, I believe 1 hits at 3. If I'm going between 0 and 3 halves, I'm pretty sure 3 halves is the intercept. Which area can I find perfectly and exactly?
Triangle.
Yes! 1/2 base times height. My height is 3 because of the intercept. My base is 3 halves because of the other intercept. I have 1/2 times base times height. Area equals perfectly. Done. What about this? Can I say the area is between the bigger rectangle with a height of 3 and a base of 1 and the smaller rectangle, which is a height of 2 and a base of 1? Can I say the area is between 2 and 3 because of the smaller rectangle under it and the bigger rectangle over it? Yes. But do I know exactly what that is? No. But what I can tell you, even if you don't fully understand what or how or why, the area will be the definite integral between 0 to 1 of x squared plus 2dx. What is that number? Ours is not to know it quite yet. But I can show you how to solve for it. Not how as in we've learned a definite integral, but at least an expression that represents it. Jared, when he wrote down in his notes, or showed in his notes, or talked through in that example, a definite versus indefinite integral. A definite versus indefinite integral. A definite integral has a lower bound starting point, an upper bound ending point. But here's the weird thing. Didn't I say this was technically a sigma with an infinite bound? Technically a sigma with an infinite bound. Let me show you one more thing. Another way of writing this would be the limit as n goes to infinity from I equals 1 to n of f of c sub I times delta x sub I. And even better, I could say that this is the limit as n goes to infinity I equals 1 to n of c sub I squared plus 2 times delta x sub I. And I'll leave it right there for now. Anybody have any idea as to where I'm getting f of c times delta x? Now f is the function, like that gets plugged in, but why am I saying a y value times a change in x value? A y value. What are y's called? What's the y of a function called? At a certain x value, the y is the function's vertical displacement. But what's another snazzy like geometry term for vertical displacement or vertical position? Oh, that's a height. And what's a delta x?
Change.
Horizontal displacement, vertical displacement. Isn't that a base times a height? And isn't a base times a height just a rectangle? Delta x's are bases. F of x's are heights. Bases times heights are rectangles. But wait a minute. How many rectangles are we finding the area of? What's n approaching? So how on earth can a definite area between 0 and 1, a defined, restricted, finite area, be using an infinite number of rectangles to find it and define it perfectly? We'll find out tomorrow. All right, cool kids. Tonight, finish up your motion packet. I will see you later, skaters.